Let us summarize the whole sampling theorem. What are the important and salient features of this particular topic, and then let us go through some multiple choice questions in this session. Okay, let us start with summarizing what we have read so far. Okay, what is sampling? Sampling is the process of converting a continuous time signal into a discrete time signal. That is called as a sampling. And what is sampling period? Sampling period, or is also called a sampling interval, is the time interval between successive samples. And sampling frequency is a reciprocal of sampling period. It indicates the number of samples per second. So, let us say I have a continuous signal like this. So, this is a continuous time signal. I convert this into a, let us say, some discrete signal. Okay. So, this conversion of a continuous time signal, okay, into a discrete time signal. Okay, let us say this is 0, this is 1, 2, 3, 4, 5. So, this is a discrete time signal, and this is the sampling time, or we call it as a TS. Okay, this is the separation between the two samples. So, when I can get the sampling frequency as 1 by TS of this. So, this is what is called a sampling. So, basically a continuous time when it is converted to discrete time with a certain time period, that is called a sampling period, and reciprocal of that gives us the what is the sampling frequency, and this is in samples per second. So, this is how a sampling application converts a continuous time signal into a discrete time signal. Now, let us define a sampling theorem. Okay, what is the basic sampling theory? Already we have done this, we are just summarizing this. Okay, it is also called as uniform sampling theorem, or it is also called as a low pass sampling theorem. As you are aware, earlier we have also seen the sampling theorem for band pass signals also, but let us start with a low pass sampling theorem now. It is also called as uniform sampling. During the course of this summary, we will find out why it is also called as uniform sampling. Okay. So, what does this sampling theorem says? A band limited signal x of t with x of omega is equal to 0 for omega greater than omega m can be represented into and uniquely determined from its samples x of nt if the function sampling frequency fs is greater than or equal to fm. So, basically we are talking about a signal whose frequency component do not exist beyond a certain value. That means, you have an x of t, okay, and the x of omega, this will be 0 for omega greater than omega m. That means, for certain frequencies beyond which x of omega does not exist. That means, we are talking about a frequency where omega is considered to be a low frequency. So, this is applicable for a frequencies which are low pass frequencies. Okay. So, this is why this sampling theorem is valid, and again what is the sampling rate? That must be equal to or greater than 2 FM. Generally, because it is very difficult to find ideal low pass filters, so what we do is we generally go beyond a certain value above 2 FM, some value which is a little greater than 2 FM, so that even if you use some real time filters, they will be able to distinguish between this different frequency parameters. This is about a sampling theorem for low pass signals or low pass frequency signals. Let us now see one basic question. Why sampling theorem is called as a uniform sampling theorem? As I said earlier, why a sampling theorem is called as a uniform sampling theorem? Let us see. Because it applies to signals which are sampled at uniform interval rates. Why it is called sampling uniform? Because signals which are sampled at uniform interval rates. We see the sampling is done at a uniform rate, isn't it? The TS is neither increasing nor decreasing, so it is uniform throughout. That means the sampling rate is constant. That is why this is also called as a uniform sampling rate. Let us see the next question. Why it is also called as low pass sampling theorem? Because it applies only to the sampling of signals which are band limited. That means, I do not have frequencies above certain frequency, isn't it? That means, x of omega is 0, as we have seen earlier, x of omega is 0 for omega greater than omega m, either side. So, that means there is a limitation to the frequency components which are available. So, x of omega does not exist, so sampling theorem does not exist. That is, this is a band limited, that is why we call it as a low pass sampling theorem. Now, let us see under what conditions it is difficult to retrieve the original signal back from the sampled signals. What are the conditions under which it is impossible to retrieve the signal back? The whole idea is take a continuous time signal, sample it, get a discrete time, convert into some other digital form, and then back to analog form or back to the original signal. That means when I am sampling x of t to x of excess of t, that is sample signal, I should be able to get back excess of t so that I can get back my x of t. Okay? So, let us see that. When it is impossible to retrieve x of t from xs of t, where xs of t is the sampled signal. First point is when omega s is less than 2 omega m, the spectra of the sampled signal overlap, that is aliasing occurs. Let us see that. What is that? Now, what is my condition here? Omega s is less than 2 omega m or fs is less than 2 fm. When this happens, let us say I have a signal like this. You see here, I want to retrieve this, let us say. I can't retrieve because there is an overlapping that is happening here. Here also there is overlapping. So, retrieval of the signal, this is excess of t, let us say. I cannot get my x of t because of this overlapping. This is called as aliasing effect. Okay. So, it becomes impossible for us to retrieve. This is one condition. So, what is that we have said? So, to retrieve, I should make this fs greater than or equal to 2 fm. In fact, greater than 2 fm can be an ideal case. So, that means they will be separated, then you can easily retrieve them back. Second condition we will see, if I want to extract the signal, x of t from x of t, what is that I need? Then the first point is x of t should be band limited to some frequency omega m. That means there is a band limitation to the signals. X of t must be limited to a certain band. Let us say I have a signal which is limited to a certain band only. So, this is where you have a limitation. That means your function does not exist beyond this or beyond this. So, this should be satisfied first of all. Next, the sampling frequency omega s should be at least twice the band limiting frequency omega m. So, this is my band limiting frequency. Let us say this is omega m. Okay, this is minus omega m. This is my band limiting frequency. So, what should be my sampling frequency rate? That should be omega s must be greater than 2 omega m. So, this is the condition under which I can be able to retrieve the original signal from the sampled signal. The condition under which we cannot retrieve is when I sample rate is less than the band limit, that is 2 omega m. So, overlapping occurs, that is aliasing occurs. So, we cannot retrieve the signal back. And now, when I increase my frequency, fs greater than equal to 2 fm or omega s is greater than 2 fm, that is a band limiting signal, I can retrieve. So, what will happen in that particular case? In that particular case, what happens is the signals are separated like this. Okay, the signals are separated like this if it is exactly equal. Okay, then as you see, there is no overlapping here. This signal is ending, that signal is starting. So, these can be easily retrieved. And also another condition is the signal must be band limited. If signal is band limited, then only I can be able to calculate my sampling frequency. So, band limitation is one condition where I can easily retrieve. Second condition is the sampling frequency must be twice the band limiting frequency or the maximum frequency of the signal. Let us see what is called as a guard band. When omega s is greater than 2 omega m, then the spectral replicates have a larger separation between them called as a guard band. What are we talking about? We are talking about the spectral separation. If two spectra are separated by a certain distance, the distance between those two spectra is called as a guard band. Let us see that. Now, earlier I will draw 3 cases here. Okay. Let us see this. The first case, if you see here, the sampling rate as we have seen is less than the band limit. So, because of this there is an overlap. or we can also write this as Fs less than 2Fm. Okay, what is the second case here? The second case here is where omega s is equal to 2 omega m or Fs is equal to 2Fm. If you see here, there is no gap between these two spectra. The spectra are not overlapping, but they are immediately followed by each one. So, there is no guard band. So, if you look at this second case where this is the third case where omega s is greater than 2 omega m or Fs is greater than 2Fm, what happens here is the spectra are separated by certain distances. This separation which you see here, this is nothing but your guard band. Okay, this is called as a guard band. Let us define what is called as a aliasing. Okay, we have seen the overlapping, we have defined it as aliasing. Let us define it in terms of a statement. What is aliasing? Aliasing is defined as a phenomenon in which a high frequency component in the frequency spectrum of the signal takes identity of a lower frequency component in the spectrum of the sampled signal. So, what does it say? It says as the phenomenon in which a high frequency component in the frequency spectrum of a signal takes identity of a low frequency component in the spectrum of the sampled signal. So, the high frequency spectrum is taking identity of a low frequency spectrum in a sampled signal. This is called as a aliasing effect. How does aliasing occur? Okay. So, we have seen one condition. Let us put it on again this point here. The first point is the signal is not band limited to a finite range. That is, there is no omega m properly defined or no Fm properly defined. This first. The sampling rate is too low. That is, Fs is less than 2Fm. That is 2. Sampling rate Fs is ideally should be as per Nyquist's theorem, it must be greater than or equal to Fm. But if it is less than that, that is sampling rate is too low, aliasing occurs. How can I avoid aliasing? The first point I can avoid aliasing is x of t must be band limited, the sampling frequency must be greater than 2Fm. So, these are the two conditions under which I can prevent aliasing. We also seen another condition under which aliasing occurs. First is there is no band limitation, the second is poor sampling. How to prevent? We have to band limit it. Second point is sampling rate must be high. High means what? Greater than 2Fm. Let us see what are the effects of sampling rate. The first point, xs of f is a repetitive version of x of f with x of f repeating itself at regular intervals of Fs, the sampling frequency. Okay. So, let us see this on the board. What is happening here? We are saying that xs of f is a repetition of x of f at a sampling rate x of f. We have seen this. Let us say this is the first repetition. The second repetition is happening here. The same signal if you see is being repeated, isn't it? So, let us say this is happening at a certain frequency Fs, okay, and this is happening at a certain other frequency which is 2Fs. So, they are repeating. The same thing happens this side also. So, this is what we mean by a sampling rate. That means, the x of f is repeating every time. So, this is xs of f, this is a sampled version, and whereas this is x of f. So, x of f is nothing but a repetition of xs of f is nothing but repetition of x of f at a sampling frequency Fs. This is how it happens. Okay. So, let us just redefine that again. After seeing this, let us repeat this. What is xs of f? Is a repetitive version of x of f with x of f repeating itself at regular intervals of Fs, the sampling frequency. So, this is x of s repeating this side, the same thing repeat this side also. So, all these repetitions combined together will result in xs of f. That is the first point. Let us see the second point. If Fs is greater than 2Fm, then there is a guard band and it is easy to separate x of f from xs of f. So, we have seen this earlier also. So, if I make my sampling frequency greater than twice the maximum frequency, then there will be a guard band that exists. It is easy for us to separate the x of f from xs of f. So, let us just see this again once more. So, what happens here is, let us say this is the 1 and this is the 1 here, and again let us just put it here one more. Okay. Now, the existence of guard band here, this again depends on what? The guard band existence depends upon my rate of sampling. If I sample it at a rate greater than twice the maximum frequency, then the guard band exists. When this happens, I can easily retrieve this because there is no overlapping or zero separation between these two. If I make this exactly, the separation guard band will be equal to 0. And when this is less than sampling 2 FM, what happens? There will be overlapping, so cannot distinguish between two signals. So the guard band existence helps us in retrieving x of f from xs of f. Let's see the third point. If fs is equal to fm, that is Nyquist rate, no guard band exists and an ideal low pass filter is needed to recover x of t from xs of t. Fine, we have seen this again, isn't it? So if I make it exactly equal, fs is exactly equal to fm, what happens? There is no guard band and also there is no overlapping. So what I need an ideal low pass filter to separate, isn't it? So getting an ideal low pass filter is difficult. So what practically we do is we make sure that fs is slightly greater than 2 fm, so that guard band does exist. Then again there is a limitation to amount of oversampling. If oversampling is in, as we see shortly now, if oversampling happens, what happens? The bandwidth requirements will go up tremendously. Okay. Then comes to the fourth point. If fs is less than fm, aliasing takes place and it is not possible to recover x of t from xs of t without distortion. So we have seen all this, isn't it? So if I undersample, aliasing occurs. If oversample, oversample in the sense fs is greater than 2 fm, then guard band exists, easy to separate signals. And if ss is exactly equal to fm, we need an ideal low pass filter to separate. So these are the very important points and they are all depend on the sampling rate. Okay. Let us just redefine what is Nyquist rate. Nyquist rate is a theoretical minimum sampling rate at which a signal can be sampled and still be reconstructed from its samples without distortion. Nyquist rate is a theoretical minimum sampling rate at which a signal can be sampled and still be reconstructed from its samples without distortion. Okay, that means the minimum sampling rate is required. What is the main criterion of using a sampling Nyquist rate? When I sample, I should be able to retrieve back my signal back. So this is called as the minimum sampling rate. Okay, that's what Nyquist rate talks about. And there are two types here, oversampling and undersampling. We have been using that word very frequently, oversampling and undersampling. What happens if I oversample, or what is actually oversampling and what is undersampling? Oversampling is a sampling signal at a rate greater than the Nyquist rate, that is fs is greater than 2 fm, that is called as a oversampling. Undersampling, sampling a signal at a rate smaller than Nyquist rate, that is fs is less than 2 fm. So I can oversample it and undersample it, but we should be very careful how much do I oversample. And let us define what is called as a Nyquist interval. Nyquist interval is a time interval between any two adjacent samples when the sampling rate is Nyquist rate. That is, what is the distance between two samples, or what is the time interval between two samples is called as a Nyquist interval. Let us define what is an anti-aliasing filter. Anti-aliasing filter is a low pass filter used for band limiting a signal before sampling. Okay. So we use this low pass filter. What is the function of this low pass filter? It is primarily used for preventing aliasing. Anti-aliasing filter is a low pass filter. We said aliasing occurs, one condition. Why? There is no band limit, we said the first point. So what is the solution to this? I pass a signal which has no band limitation through a low pass filter. And what happens? The output of the low pass filter is a signal which is band limited. So this itself is preventing anti-aliasing. This is one condition, isn't it? The other condition is, as you are aware, fs must be greater than or equal to fm. The first case is where I pass a signal which has no band limit through a low pass filter. So this low pass filter is also called as a anti-aliasing filter, and its primary duty is to prevent aliasing. Let us see what are the disadvantages of sampling a band pass signal f1 to f2 with fs greater than 2 f2. Okay, you have a band pass signal existing from f1 f2 and I am sampling at a rate which is fs greater than 2 f2. Let us take a band pass signal. Let us say you have a signal here, this is f1 and f2. Okay, my sampling rate is greater than 2 f2. What are the disadvantages of this? We will just see now. The spectrum of the sampled signal will have spectral gaps. That means there will be a lot of gaps between the different sampled versions of the output, because we are doing at a rate greater than f2. So f2 is large, the sampling rate is also very large and therefore have practical limitations. If f2 is very large, what happens? We have a spectrum which is existing from, which has a lot of interval between the samples. So when interval sample is more, they have a practical limitations. That means it will be very difficult to define a filter for that type of samples, because the guard bands are huge, spectral components are existing at very high frequencies, they are separated from large intervals. So, this will result in practical limitations. So, let us now define a sampling theorem for a band pass signals. Okay, let us define something. So, earlier we have defined sampling theorem for a low pass signals. Now, let us see what happens to the sampling theorem, what are the modifications which we have to do in sampling theorem to see that is applicable to band pass signals also. Now, let us define this. If the bandwidth of a band pass signal x of t is equal to b, which is given by f2 minus f1, that in fact is equal to fm, then the signal can be recovered without any error if the sampling is done at a rate of twice the bandwidth, that is fs is equal to 4 fm or ts is equal to 1 by 4 fm. So, here we take a band pass signal, calculate its bandwidth, then that bandwidth is equal to twice your modulation frequency, twice the maximum frequency, that is 2 fm, and our sampling rate here must be twice of that, that means 2 into 2 fm, that will be 4 fm. So, that means I take a band pass signal here, this is f1 and this is f2, I calculate the bandwidth, okay. The bandwidth, this is equal to f2 minus f1 and this is equal to fm, then my sampling rate, Nyquist sampling rate must be equal to 2 into 2 fm, that is 4 fm. So, this is what the sampling theorem, slight modification in the sampling theorem for a band pass signals, where the sampling rate or the Nyquist rate is 4 fm, because the bandwidth of the given signal is 2 fm. So, that will be twice that. So, similarly you can calculate Ts also. So, what will be the time rate? That will be equal to 1 by 4 fm. This will give me the sampling interval between, or Nyquist interval in the band pass signals. Let us see what is called as an interpolation. What is interpolation? Interpolation is a process of reconstructing a continuous time signal from its sample is called as interpolation. The process of reconstructing a continuous time signal from its sample is called as interpolation. So, what is that? Convert x of t into xs of t, that is called as sampling, and constructing x of t from x of t, xs of t is called as interpolation. X of t to xs of t sampling, xs of t you have, and I want to reconstruct back my x of t, that is called as a interpolation. Then we see what is called as zero order hold. The zero order hold is an interpolator which reconstructs the continuous time signal from its samples by holding a sample value constant till the next sample is received. So, zero order hold is an interpolator actually, which reconstructs the continuous time signal from its samples by holding a sample value constant till the next sample is received. Then see what is called as an aperture effect. Aperture effect is the distortion wherein the amplitude of the high frequency components are reduced relative to the amplitude of the low frequency components in the reconstructed signal x of t obtained from the flat top sample version of the signal. Okay, we have seen what is a flat top sample earlier. So, aperture effect also we have seen. What is that means? There is a variation in the amplitude. The high frequency components have a lesser amplitude compared to the low frequency components of the signal in a flat top sample. This is called as a aperture effect. So, what is an equalizer? Equalizer is a device used in cascade with the reconstruction filter to reduce the distortion within the message frequency band, that is called as an equalizer.